Okie dokie, let's get started. So thanks for joining me at 8 a.m. I just did the review session until 10 and went home and slept and then came back. So I should have just slept under my desk or something. All right, so we're just gonna do review. So we're gonna just continue on with the packet. I love review because I allow myself to sit. So yeah, so in the review session last night, we basically did all of chapters 16 and 17. So I do want to spend some time on 15. So students, I guess, thought that 15 is easier, but it's all K. It's all big K. So all the same concepts still stick, but I know that there's a lot of tough conceptual ideas of like, weak acids, what are the stronger weak acids, and then, what conclusions can we make about the conjugate base. So I will do some more acid stuff as well and review those things, but let's do chapter 15 stuff. And as a reminder, okay, our midterm 2 is tomorrow at, what time is it? Can someone tell me what time? 5:30? Is that 5:30? Okay, so 5:30 in Hitchcock 131. All right, so 5:30, Hitchcock 131. Remember, it's just our classes in that room, so it's not so crazy busy. The top balcony is probably going to be off limits, but that's okay. There's enough room for all of us in the first floor. If you feel like you're cramped in that space, sit towards the front. No one ever likes to sit towards the front. They walk into the room and then they like sit at the first desk that they see. So there's lots of empty seats in the front if you want more space. So just FYI. All right, and then I'll be there to cheer you on, and then you can look at me and maybe hear some of my idioms that I use during the exam. All right. And something I mentioned yesterday at the review, this midterm 2 is actually pretty high scoring in terms of all 3 midterm exams. I think it's because of all the math. So I'll try to, not focus on the math part, but, help you recognize today what strategies you need to arrive at the answer. I'm assuming that you know how to do the algebra, so let's focus on the strategies. All right, so we're starting with the Zoom packet. So we'll do chapter 15. We'll just go in order. All right. So we have an equilibrium constant for this reaction. Kc is this number at this temperature. This system at equilibrium has these concentrations. Here's the reaction. What is the concentration of methane at equilibrium? So this question, I want you to recognize, okay, we're given K. All right, and what does K tell us? K tells us, in general, the ratio of products over reactants at equilibrium. So this question, when they give us concentrations, are these concentrations at equilibrium? Yes, they are. So you just plug in these numbers into the K expression because they are already at equilibrium. No ice table needed. The only hard part, I guess, is constructing the K expression. So recognize that Kc, if it's Kc, what does the unit inside K need to be? They have to be molarities, concentration, versus Kp, you use what? Pressures, typically in ATM. All right, so Kc is equal to products over reactants. So CH4, concentration, H2O, over concentration of H2. H2 to the 3, yes, and then CO. And just as a reminder, gases can have concentrations. Remember Pivnert, PV equals nRT. Gases, they obey most, ideal gases, they obey Pivnert. Molarity is just moles per liter, right? And so we can rearrange Pivnert in this way to get N over V equals, what would it be? I can't math. P RT. RT is a constant, so what we see here is that pressure of your gas is proportional to N over V. N over V is molarity. So that's the idea here. Molarity is proportional to pressure, where we just have this RT term, and that would be constant for a particular reaction at a temperature. And so this is what gives us our KP/Kc conversion, which we'll do in the next question, I think. Oh no, in part B. All right. So we just plug and chug. All right, we just plug and chug, and what are we solving for? Methane, that's it. All right, just do not forget, the stoichiometry in the chemical reaction has to propagate itself into the K expression. So that's the idea here. So I'll just set it up. So K in this case is 3.93 equals X, whatever that methane value is, and then just put the values in the correct place. 0.0478 over 0.1566 cubed. Do not forget that cubed, because if this was a multiple choice question, we would have the answer where you don't cube that. All right, so don't fall for that. And then times 0.1522. All right, so the reason we don't need to do an ice table is because they give you equilibrium concentrations. All right. So what is the Kp value of this temperature, at this temperature? So are we given this equation on the equation sheet to do a Kp Kc conversion? Yes, we are, but hopefully you know it by now. The Kp Kc conversion is Kp equals Kc RT delta N. All right, and the idea here is we need to recognize, okay, gases are being formed in this chemical reaction. We need to calculate what delta N is, so the change in moles of gas for this reaction. So you subtract product moles minus reactant moles, but only for gases. So in this case, there's 2 moles of gas on the product side, 4 on the reactant side. So delta N is -2. All right, and so we just plug everything in. So Kc, we are given that 3.93 times R. Which R do we use? The 8.31 or the 0.081? 0.08. Why? Why? Did you just memorize that? Yeah, okay. Sure, but it's also in the unit. So remember when we used Pivnert, we almost always use the 0.08206 number because the unit was liter ATM mole Kelvin. We only use the 8.314 joule one when we're working with energy. I hope that you've recognized that by now. We'll use the other R in the next chapter. All right, so 0.08206 liter ATM mole Kelvin, but I don't feel it writing the unit, times the temperature. This does need to be in Kelvin, just like our Pivnert stuff, to the -2. All right, and then there's your answer. All right, and so why do we have this RT business here? The reason is you can think about, okay, this is our K expression. They're all in molarities. But we said, molarity is equal to pressure over RT. So depending on how many moles of gases are in this expression, we're just applying the correct number of RTs to this expression. And that's where this equation comes from. The RT delta change in moles of gas here is how we account for those RTs that we would use to convert all of these. So you could, in theory, have each of these molarities convert each one to a pressure at this temperature, but this equation does the exact same thing as well. Okay, great. Okay, so side question, because I always like to have different things. What if the reaction was this? What if I had like a carbon in there? What would delta N be in this reaction? Pretend that it's balanced. What would it be? What would delta N be? -3? It's still -2. It is still -2. I did not change delta N because delta N is change in moles of what? Everything? No, it's only change in moles of gas. Is carbon a gas? No, so it is still 2 - 4. All right, so don't include, if there's a solid present, do not include that in your delta N calculation. Actually, here, let me preface this a little bit different. If this was the balanced reaction, would carbon be in the K expression? No, it wouldn't. All right, so that's why it's not a part of the delta N calculation as well. Yeah, question? Does aqueous solutions count as well? No, they don't. In delta N, they don't count as well. The reason is because if you have a molarity in here, so let's pretend, CO was aqueous, in this reaction. Does CO, if it's aqueous, have a pressure? No, it doesn't. So we don't have to do this RT business in it. So that's why it's not in delta N. All right. Okay. Yeah. So that's like kind of conceptual there. Good. All right. So let's keep going. All right. So we have, it's the same equilibrium. And see, it's at the same temperature. So 1200 Kelvin. Would Kc still be 3.93 if we weren't at 1200 degrees? What if we were at 1000 degrees? Would K be the same? Can we use the same number? No, we can't. All right, so just throwing in some conceptual things in there. All right, so the equilibrium constant is blah. The system is made up of 1 mole each of these things in a 4-liter container. Is the system at equilibrium? So we need to basically guess and check here. All right, so let's, so they give us Kc, so I think the best thing, course of action would be to calculate the concentrations of everything. So since it's made up of 1 mole each of these things, what is the concentration of hydrogen? Is it 1 molarity? No, it is 0.25 molarity. So 0.25 molarity for each of these things, right? Because remember, molarity is equals to moles over liters. And because this is in a 4-liter container, we can't just plug in that one. So 0.25 for each of these. So then we just guess and check and plug those numbers into the Kc expression, which we already did up here. So I'll just copy that because I'm lazy. All right, and then just plug in the numbers. So we're just going to put in 0.25 for all of them. So 0.25 squared over 0.25 to the 4th, since it's the same number over and over and over again. And I think, what do you get? What's my key? 16. So you get 16. Is this at equilibrium? No, it's not. So let's for a second pretend that you didn't factor in the volume, okay? So I want you to recognize this is Kc. So we need concentrations. So pretend like, your friend did this question and they just put 1 mole. Instead, they thought the concentrations was one mole. So when you would go and calculate what we think is Q, all right, what we would think is Q, wouldn't you get 1 squared over 1 mole to the 4th, and then you would get 1? In this case, this would be incorrect. This would be incorrect because you used mole amounts, not molarities. And so this would be a tricky question, all right? That recognizing, hey, you need to convert to molarities because this is Kc, so you need molarity. So do not just stick in 1 and see that we get a different number, and then our answer would be a little bit different. All right, okay, all right, so that's incorrect. Don't do that. All right, we used molarities. Q is 16 versus what? Our K is about 4. So which way is this reaction predicted to shift? And so I personally don't memorize, if Q is bigger than K, then the reaction shifts this way. I just recognize, okay, Q is equal to 16 over 1. K is 3.93 over 1. When you calculate K, it's always products over reactants. So in the system right now, I have too much what? Products, yeah, because my numerator is too high. So the reaction has to shift towards the reactant side. So that's how I would predict it. So reaction shifts to the reactant, so it's shifting left. So that's how I think of it. Or if you just want to memorize, okay, when Q is bigger than K, it shifts to the left, but I don't like memorizing things. All right, just recognize that those expressions, it's always products over reactants. Okay? Or, if we calculated Q, pretend you did it wrong, and we thought Q was 1. All right, so let's do it the wrong way. Let's think, okay, Q is 1. So I like to put it, make it a fraction and recognize, okay, if we're comparing 1 over 1, and we're comparing that to Q, comparing that to K, which is usually 4 over 1, In this case, I have not enough products. And so if I have not enough products, the reaction needs to shift to the right in this case. So if you did it wrong, you would get the wrong answer. Yes. Okay. All right, good. Is that good? Okay. All right. Okay. All right, so how would we approach this question? Here are some reactions. Here are the K values. So the K value for the first one is 4.5 times 10 to the negative 4. For the second one is 1 times 10 to the 14. What is the equilibrium constant for K, the third reaction? So what's your strategy here? How do you want to work this question? I hope in your mind you recognize, oh, this is like Hess's law. It's just like Hess's law, but what's the difference? Instead of adding up enthalpies, you multiply the K values instead. All right, so I just focus on the target reaction and try to puzzle it together. I'll focus on one thing at a time. So right now I'm gonna look for HNO2 aqueous and see which equation it's in. So it's in the first equation. Is it on the right side? Yes. Is it in the right quantity? Yes. So we don't have to do anything to that reaction. Just leave it as is. All right. What about the second reaction? Oh, we don't have to do anything to that one either. All right. So what would we do to the K values? We just multiply them together, and that's the K for the second or for the third reaction. All right. So let's pretend we did have to change reaction 1. So pretend for a minute we did adjust reaction 1. If we flip a reaction, what do we do to the K value? Do we multiply it by -1 like we do Hess's law? No, you take it to the -1 exponent. What if we double a reaction? What do we do to the K value? You square it, all right? What if we have to reduce a reaction by a third? You take the cube root, but so cube root, on the calculator is sometimes hard to find. So another way you can write cube root into your calculator is just take it to the 1/3. That's another way to do it, okay? All right, because what if you had to reduce a reaction by a fifth and you have to take the 5th root? I don't know where that key is on my calculator, and I'm not gonna take precious time to find it. So I should be able to recognize, oh, okay, to take a 5th root, you would just take that value and take it to the 1/5. It's the same thing. All right, so that's to save time. It's the same thing. Okay. See, I'm not very good at teaching math. I'm good at teaching chemistry, but my eggs aren't in the math basket. Or biology. I'm very bad at biology. All right. Okay, so we have A. In a 1-liter container, we heat it to some temperature. A decomposes according to this reaction. At equilibrium, the concentration of B is blah. Calculate Kc. Great. So this is an ice table. This is an ice table. So question 4 is different than question 1, because question 1, I just straight up give you equilibrium concentrations, you plug and chug. This one's a little bit different because I give you initial conditions and only part of the equilibrium conditions. This is what I call the Sudoku method ice table, where you just need to fill in your ice table and figure out, okay, what are the missing pieces given the information that I have. So there's the equation, all right, my ice table, initial, change, equilibrium. So I need to fill that in. So this 0.5 value, where is that gonna go? What line is that gonna go in? Initial, yeah, because that's where we put A in first and then we heat it up. So that's how much A we initially put into the container. Am I gonna put 0.5 moles in the ice table? No, ice tables need to be in the unit of molarity or pressures. But in this case, because we're calculating Kc, molarity is fine. But I made it easy for you. The volume is just 1 liter, so that mole amount just becomes molarity. Great. All right, so that's what we have in the container initially. Which way does the reaction have to go? Forward. So it's minus what? X? 2x. It's minus 2x, then plus x plus x. Yeah, so don't forget that stoichiometry. We got spoiled because chapter 16 and 17, it's always 1-to-1-to-1 ratios. But in chapter 15, it is possible to not have 1-to-1-to-1 ratios. Okay, so do recognize the stoichiometry here. All right, so do the math. 0.5 minus 2x, x. That's all the crap I have at equilibrium. So let's make our Kc expression. This needs to be in molarities, and that's what my ice table's in. So recognize, okay, we have concentration of B times concentration of C over concentration of A squared. All right, and then you can plug in your equilibrium concentrations into the K expression. So remember, equilibrium line always goes into K, always. And so what are we trying to calculate? Kc? Yeah, so the problem is when I put these equilibrium concentrations into K, I don't know what X is, but can I get X? Yes, the question gives it to us. It's the piece of information we did not use yet. It is B is equal to 0.065 at equilibrium. So this 0.065 is this value, X. So right here in our ice table, we assigned B as X at equilibrium. So B is equal to 0.065 molarity. This is X. So since now we know X, now we know part of the table, we can fill in everything else. All right, so that means that this X is also 0.065. That also means that X is also 0.065. All right, so go ahead and just fill in those X amounts and then plug it into the Kc expression, right? So that would mean that A at equilibrium is equal to 0.5 minus 2 times 0.065. And we can calculate that, 0.5 minus 2 times 0.065. It is equal to 0.37. All right, so these are the concentrations that I stick into my K expression. So equals 0.065 squared, since both B and C are X, over 0.37. And then that's my K value. All right, okay. So in this example, do not neglect X. Don't, because we got so used to it. We got so used to it in chapter 16 and 17. Of neglecting the minus X right here, but we know what X is. Don't be lazy and neglect that X. We know what it is, just plug it in, all right? So this question, I hope you see some resemblances, all right? This question, yeah, it's all gases, whatever, okay? Think about what kind of aqueous, chapter 16 or 17 question this resembles. This kind of question resembles a question where I would give you something like, okay, you have a weak acid. It has an initial concentration of 0.11 or 10 molarity. All right, I give you the pH. Let's say I say the pH is like 4.0. All right, and I ask you what is Ka for this system. This question we just did is literally exactly the same as this chapter 16 question, where I give you a weak acid equilibria, I give you the initial concentration, so this would go in your initial line. The pH is what? What's the trick with pHs? pHs are always the concentration of H plus at equilibrium. So in this example, H plus concentration would be X. So me giving you the pH is giving you what X is, all right? And so it's no different than this question we just did, all right? Where I give you X, we plug in X, and we calculate, we plug in those numbers into our K expression, you calculate Ka. And so just like in this example, do not neglect that minus X in that equilibrium line, because we know what X is. Don't be lazy, okay? We only are lazy in avoiding the quadratic. And I'll tell you, on the exam, you never actually have to do the quadratic. You can always make an approximation, always, but you just need to know how to make an approximation, All right, so are we gonna do another one? Yeah, let's do this one. So this one is, ice table, our second type of ice table where we actually have to calculate equilibrium concentrations. So we might have to do the quadratic. So in this table, I give you the equilibrium line. So there's no quadratic needed. You just have to plug in the numbers in the right places into K. But question 5 is different in that I give you an initial concentration. So in this case, pressure, I give you Kp, but now we're calculating for equilibrium. So now we're calculating for what is X. So this might require the quadratic. So let's fill this out. All right, so see how this is Kp and I'm using pressures. So our ice table can also work in pressures as well. So ice, all right, we initially start with H2S is 1.8 ATM. Which way does this reaction have to go? Forward, yes. So it's minus 2x again, plus 2x plus x. So don't forget the stoichiometry. Don't forget that stoichiometry. So at equilibrium, we will have 1.8 minus 2x atmospheres of H2S. We'll have 2x of hydrogen, and we'll have x amount of S2. Okay, great. So let's construct our K expression. So Kp is equal to the partial pressure of hydrogen, but it's squared. We need the partial pressure of S2 at equilibrium, it's not squared, over the partial pressure of H2S, and it is squared. Yay. Okay, and we know what K is. It is a tiny number, 2.2 times 10 to the negative 6. Great. So the trick with ice tables and Ks, the equilibrium line always goes into the expression. So let's fill that out. So we got 2x squared times x over 1.8 minus 2x equals a tiny number, 2.2 times 10 to the negative 6. Great. Okay, so our goal here is, what are we trying to find? Equilibrium pressures of everything. Okay, so if I figure out what x is, I can then plug everything back into the equilibrium line and calculate it. But there's a problem here. I need to solve for x, and this looks really ugly. This looks really ugly, but let's use our intuition here of what the most appropriate approximation we can make. What do you really want to do? What do you really want to do? You want to do what? You want to get rid of this minus 2x, right? And we can, but here's the reason why. Okay, K is what kind of number? Big or small? Small. So if we have a small K value, what is mostly present at equilibrium? Products? Reactants. So let's look at this equilibrium. If we have mostly reactants present at equilibrium, do we actually lose a lot of reactant H2S? Does it actually move forward that much? No, it doesn't. So 1.8 is a relatively large number. So the amount of reactant I actually lose is going to be rather small. So that's why we can make that approximation. This minus 2x is going to be really, really small. So small that it's probably not going to affect, it's not going to change 1.8 within like its actual sig figs. So that's the approximation that we're going to make it simpler on us so we don't actually have to do the quadratic. So we can do that. We can neglect this 2x because we know it's going to be really small. We're not going to lose that much of it. And then we can simplify this. Doing the math, what does the the numerator become? So doing 2x squared times x, what does that equal to? 4x cubed, yes, is the numerator, and then over 1.8 equals 2.2 times 10 to the negative 6. Yeah. Should it be what? Oh yeah, that whole thing squared. I'm sorry. Yes, it should be. Yes. Is that why everyone whispering? Yes, it should be squared. Yes. So I'm sorry about that. Yes, the denominator should be squared as well because of the K expression. I forgot to bring that down. Okay. But it still doesn't change the approximation that we made. All right, so I brought that square back down so the denominator is 1.8 squared. We just neglected that minus 2, that minus 2x. All right, so then when we solve for x, what is it? What is it? Is it a tiny number? Is it a tiny number? I get 0.0121 ATM. Is that my answer? Partially, yes, it is partially my answer. Okay, so the x I just calculated is the concentration of what at equilibrium? Just the last one. It's just the sulfur one. Oh my gosh. It's just the S2, all right? And so we just got to do a little bit of math manipulation to get the concentrations of everything else. All right, so this is the concentration of S2. Yeah, S2. Okay, so that's, or not the concentration, the partial pressure of S2. All right, the partial pressure of H2 is just going to be double that because H2 is 2x. All right, so 2x, I can do the math, 0.0242 ATM, is that right? Okay. All right, and then the partial pressure of H2S is 1.8 minus 2x. So did the pressure of H2S really change all that much? No, it didn't, and that's why we were able to do the approximation. So let's actually do the math. So 1.8 minus 0.0242 is equal to 1. How many sig figs does go out to? Just 2 decimal places. So 0.78. So it barely changed the pressure at all. It barely changed it. So that's why we're able to make that approximation. So you could, run the unapproximated thing into Wolfram Alpha, calculate for x. You'll get an x that is actually really close to 0.0121. And again, that's why we're able to make the approximation. So let me give you some examples of what approximation we could use when. So let me give myself some space, all right? Okay, so let's pretend K is really big. Let's say it's 1 times 10 to the 6th. And I say it's equal to x squared over 0.1 minus x. Can we make an approximation here? No, we can't. It's too big. This K is too big. So the idea here, K is equal to some really, really large number over 1. So x squared is going to be a really, really large number, essentially. So we actually could not make an approximation here. These are not the kind of exam questions we give you. But you could solve this. You could solve this, put it, solve the quadratic formula, actually solve it. All right, but we typically don't give exam questions like this. All right, well, so I have that one. What if I had this? Could we make an approximation? So K is still really large. So what if it was, 10 ATM minus x over x squared? Could we make an approximation here? So K is really big, so we have a lot of what at equilibrium? Products, yes, so 10 minus x. Are you going to lose a lot of your product? No, the reaction's going to stay on that side. So the approximation here, all right, is that we can neglect that top x. Does that make sense? Yeah, okay, K is a huge number. All right, so 10 is as big as the numerator can be, so it's going to remain 10. All right, let me do another one. What if it was 1 times 10 to the 6 again equals x squared over, oh crap, hold on. No, that's it, it's okay, okay. X squared over 1 minus x squared. Can we make an approximation there? No, we can't. We have a ton of products, All right, we have a ton of products, so this reaction is going to shift to the product side. So we can't actually say, oh, minus X is really small, because this reaction implies that, oh, you do reactants to products. All right, the reaction is going to move forward. You are going to lose a lot of reactant, but there's something special about this setup. Is there something special you can do? You have a square on the top and the bottom. You can square root both sides. Yes, if you square root both sides, this simplifies to 1 times 10 to the 6 square root, whatever that is, over x 1 minus x. Is that the quadratic? No, that is just algebra. All right, and so you could, in fact, solve this one. Okay, yeah. All right, so that's a special case one where there's a square in the top and the bottom, so you can technically solve it. Okay, what about this one? Let me do another one. What if it was 1 times 10 to the negative 5 equals 1 plus x squared, 1 minus x? Actually, no. Do I want to do that one? Yeah, that's fine. Squared. Oh my gosh. Okay, we'll just live in darkness. I told you guys to follow me into the dark, right? So, all right. Okay, what can we do here? Are there any approximations we can make? No, I don't think so. Well, maybe, because you could say, oh, okay, k is really small. You could neglect the bottom x, but you don't have to. This one is just like the previous one where it's a perfect square. It's a perfect square, so if you square root both sides, you can simplify it into 1 plus x over 1 minus x equals that 1 times 10 to the negative 8 square root. And I think if my math serves me correctly, you could in fact solve that. It's just algebra, yes. All right, so those are all the possibilities that it could be. Okay, and so I hope that clarifies when you can use the approximation and when you cannot. Let's do one more. Let's do one more. What if, it was like Ka, 0.18 times 10 to the negative 5 equals x squared over 0.5 minus x. So this would be like the Ka expression for a weak acid. Can we make an approximation? Yes, we can, because K is really small. You don't have a lot of product. It's mostly reactant. So we can say, okay, we can neglect that bottom minus x, leaving it where it's just algebra. Good? Good. All right. Okay, so hopefully that clarifies things. Okay, so, all right, let's move on. So consider these reactions. In which reactions is product formation favored by an increase in temperature? All right, so this is Le Chatelier's principle, where we can make adjustments to chemical equilibria and we can predict how things shift. So this is we're changing temperature here. Did you do LCP already? Yes, okay, perfect. So you saw it firsthand, right? Where you put your test tube in the cold water bath, the hot water bath, and then you could just make it change color forever, infinitely. Wasn't that cool? Okay, was it a pretty color? Yes, okay, good, good. So hopefully you can see how temperature affects chemical equilibria. So there's kind of two ways to think about temperature and chemical equilibria. There's the quick and dirty way to do it, where you just treat heat as a product or reactant, and that can appropriately help you predict how the equilibrium shifts. But remember that changing the temperature of a reaction actually changes the value of K. All right, and so K is actually changing, and that is why your chemical equilibria is shifting. So this question doesn't require you to understand that. The K value is shifting. All we really care about is which way is the reaction shifting. So the quick and dirty way is perfectly fine to approach this question. So depending if the reaction is exo or endothermic, we'll tell you where to put your little triangle to treat as either a product or a reactant. So in the first reaction, where does my little triangle go? On the products or the reactant side? Products, yes, because it's exothermic. All right, so if we added heat to this reaction, which way does the equilibrium shift? To the left, to the reactant side. So just the quick and dirty way is fine enough for this question. So triangle for number 2 goes on the reactant side, 3 product side, number 4 reactant side, number 5 product side. So we are looking for the case where product formation is favored by an increase in temperature. So which reactions will shift to the product side when we add heat? Which numbers? 2 and 4, yes, because heat, our triangle, is a product. All right, let me change the question. What if I said, consider the following reactions. Which cases is product formation favored by a decrease in temperature? How would my answers change? So decrease in temperature. So instead of adding triangle, what are we doing? We're removing triangle. Okay, so which reactions, when we remove triangle, does the reaction go to the product side? Still 2 and 4? No, 2 and 4. When you remove triangle, it's going to go to the reactant side. So now our answers are 1, 3, and 5. 1, 3, and 5. Okay, good? How else could I change this? I could say, which cases is reactant formation favored by a decrease in temperature? So again, we are removing triangle, looking for cases where it shifts to the reactants, all right? Good? All right, perfect. Let me change the question. Let me think about a question, all right? Which reactions will favor the products when we have the volume of the container? Which ones favor products when we have the volume of the container? Because most of these are gases, right? Yeah, they're all gases. All right, so let's think about this. Let's think about this. So since we're changing volume now, do we care about enthalpy? Do we care about triangle? No, we don't care about triangle anymore, so we can just ignore these. When we have the volume of a container, what do we do to the overall pressure? It increases, yeah. So we are increasing the partial pressures of everything. Of all the gases, sorry. We're just increasing the partial pressures of all of the gases. All right? So if you think about it, okay, you're increasing all the partial pressures that were once at equilibrium. In order for the reaction to achieve equilibrium again, the reaction will try to relieve itself of that increase in pressure. So just based upon that, how can the equilibrium relieve itself of the extra pressure? It moves to the side of the reaction with less moles of gas. Yeah, so let's inspect it. I don't know what my answer is here. All right, so if we increase the pressure of 1, which way is it going to shift? To the left or the right? To the right, yes. Because to relieve itself, it's going to make less moles of gas. It's going to move to the side with only 2 moles of gas instead of 4. What about number 2? It's going to move to the left or to the products. So because there's only 2 moles there. So yeah. So number 1 is right because we went to products. Number 2 we went to reactants. Number 3 is going to move to products, yes, because there's less moles of gas on the product side. Number 4 is going to move where? Nowhere, yes, it's going to stay the same. Okay? There's nowhere it can relieve itself. So in this example, in number 4, when you change the volume of the container, does Kp, do you make a Q? Yeah, you're still at equilibrium. So when you have the container, you increase the total partial pressures, your Q that you would calculate actually is still K. So that's another example, or like conceptually, that no shift will happen because we actually didn't change Q at all, or K. All right, and then same thing with 5. So both of those won't have any equilibrium shift. Okay, good. All right, so there we go. All right, so let's keep going. Consider this reaction. This reaction's an elementary step. I had a mistake in the key, but I updated it, so just be aware of that. So what I have up here is the updated version. So, yes, okay. Yeah, so thank you for pointing out the mistake I had. Yeah. I for some reason, I thought I was working with CO, and so I was treating it like a product, yeah. Okay, great. Okay, great. I kept referring it to as a product. So anyway, okay, so let's look at this reaction. So let's apply the ideas of Le Chatelier's principle, but extend past that and think about, okay, when we disrupt an equilibrium, what are we really doing to that equilibrium? Yes, a shift happens, but why? So let's say we remove some CO2 from this container. So if we remove CO2, we're removing what? A reactant. Yeah, so if we remove a reactant, just like we removed triangle, which way does the reaction shift? To the reactant side. Okay, yes, it shifts to the reactant side. So to the left. Great. But why does it shift to the left? Why? So let's think about what a chemical equilibrium is. Why do we use these funny arrows? Why do I take the time and draw a double arrow with a chemical equilibrium? How is this so different than like a straight up this kind of arrow? Okay. Yeah, so a chemical equilibrium is happening. The idea of a chemical equilibrium is we're saying, okay, the rate of the forward reaction is equal to the rate of the reverse reaction, right? So remember when we did mechanisms, and you all love doing mechanisms in chapter 14, okay? And the strategy we used to get rid of an intermediate, what did we do? We usually set the fast step. We said, oh, okay, forward rate law equals reverse rate law. That's exactly what we're saying here. This is a chemical equilibrium where this forward-reverse reaction is happening really, really fast, back and forth. So that's what we're saying. Rate forward equals rate reverse. So remember rate laws, okay? If this is an elementary step, what is the rate law for the forward reaction? KF. So the rate constant for the forward reaction times what? Reactants. So what are our reactants here? CO2, but two of them equals K reverse. So reverse rate constant. So these are small k's, baby k's, right? Times the concentration of the product. So CO squared O2. There we go. Good. All right. So what I just built right here is exactly what you would have done if this was a mechanism question in chapter 14 to get rid of an intermediate or something. All right. I just said forward rate law equals reverse rate law. Use the KF or K reverse and the concentrations of products and reactants. Cool. So when a system is at equilibrium, this is true. This is true. And it'll just stay true. The overall rate of the forward equals the overall rate of the reverse. If we rearrange this, we can see some interesting stuff come out. If we kind of consolidate our K terms, we can see, oh, K forward over K reverse is equal to products over reactants. So CO squared times O2 over CO2 squared. What's special about this relationship? That's K, big K, all right, equals the ratio of baby Ks equals the ratio of products over reactants. That is the significance of big K, chemical equilibria. This big K tells us, so this would technically be Kc, is the concentration of products over reactants, but it's also the relative ratio of the reverse and forward rate constants. And that's a small concept that you don't always need to know, but this is a concept we do test on. Okay, so let's actually answer the question. Why does this equilibrium shift? We need to pick the reason that explains why this reaction shifts to the left, to the reactant side. Why? Why does it shift? Is it because the reverse rate is increasing? That this reverse reaction is kind of overtaking the forward reaction, and that's why we see an overall shift to the reactant side? No, not quite, because how did we change this chemical equilibrium? We removed what? A reactant, CO2. So if we look at this rate law, What side of the reaction are we messing up? We're just messing up the forward reaction. So in this case, the rate of the forward reaction is doing what? Is decreasing, yes. So the forward reaction isn't going as fast. But does the reverse reaction change too? No, it stays the same because we're only removing CO2. Is CO2 in the reverse rate law? No, it's not. So the reverse reaction is going just as fast as it was before, but it's just momentarily the forward reaction slows down a bit. All right? So if the forward is going slow, the reverse is going just as fast, we still see an overall shift to the reactant side. All right, so that's the idea there. But oftentimes students will think, okay, if the reaction is going towards the reactant side, then the reverse reaction has to speed up. But that is not consistent with the rate law, right? Even though, yes, if the reverse reaction speeding up would result in an overall shift to the left, yeah, it's not consistent with the rate law. All right, so what's the answer? Because the forward rate decreases. That's the reason. That is the reason. It's not because the forward rate decreases more than the reverse rate. Because is the reverse rate decreasing at all? No, it's not. So it's not affected. All right? It's just the forward one that's being affected. All right? So A is the answer. Okay. All right. Let's keep going. All right. So same reaction at 80 degrees Celsius. So let me just, or 800 degrees. Kelvin, I mean. All right. So let's, there's my reaction. So we heat the reaction. Which way does the equilibrium shift? So we can just do the quick and dirty way here. So this reaction is endothermic. So where does triangle go? Reactant. So if we heat it, we're adding triangle. So the reaction goes to the products. Goes to the products. But why? Is it because we added triangle? No, it's not because we added triangle. So this is where we actually have to consider what K means, what big K, what chemical equilibrium is. So let's look, let me just copy this, okay? All right, so K is equal to products over reactants, yes, but that's not what we're focusing on here. We're focusing on this other ratio of K. K is also equivalent to the forward rate constant over the reverse rate constant. So let me just think about this conceptually. So pretend we had a really big value of K. It was big, 1,000, whatever. What do we have a lot of? Products or reactants? Products. Okay, so if we have a lot of products present, what's faster? What's bigger, the forward rate constant or the reverse rate constant? How do I want to say this? Yeah, yes. What would be faster, the forward rate constant or the reverse rate constant? If K is big. If you make a lot of products, the forward rate constant is going to be really fast. That the rate of going forward to make products is going to be really large. But you can also see that here, right? You told me, okay, if K is big, the numerator is big. Lots of products. But we can also say that about this KF, K reverse ratio. If K is big, the numerator is big. What's in the numerator? The forward rate constant, rate constant. So here's another way to think about it. All right, here's a, here's reactants, products. So think back if this was chapter 14. Or maybe we liked 14, I don't know. I like 14. Okay, so if this was chapter 14 and I asked you, which rate constant is faster, which is the faster rate constant for this reaction? The forward, that the forward reaction is the smaller hill. The forward reaction has a smaller activation energy, right? Versus the reverse reaction has a really large activation energy. So here's another way to think about this. If you put 100 children onto this playground and you just let them run around like crazy and you looked back of like where all those children were, maybe an hour later, where would most of the children end up? On the product side, yeah, they would all end up here in this kind of like energy dip. They'd all end up over here. That's a big K, all right? Because you have a lot of products. All the children, they go up over this hill. They end up on the product side there, all right? And that's what this whole expression is saying, is if we have a big K, we have lots of products, but also the forward reaction rate constant is a lot larger. Okay, so what does all this have to do with this? All right. In what direction does the equilibrium shift? Yes, we said, okay, the reaction goes to the products, but why is there a shift in the equilibrium? Is it because heat is a reactant? No, that's too simple. I told you that's the quick and dirty way to do it. The real reason is because the value of K changes. But why does the value of K change? So remember, K is equal to forward rate constant over reverse rate constant. Oh, actually, is this energy diagram consistent with this chemical reaction? No, it's not. This is what kind of reaction? Exo. This is endo. So I actually need to change this. I need to change this. So I'm going to go boop, boop, there. 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 All right, so that's reactants, that's products. Okay, so now let me ask you, if I compare the rate constant for the forward and the reverse reaction, which one's faster? The reverse, yeah. So the rate constant for the reverse is faster. If you put a bunch of children on this playground and you let them go crazy, where are they all going to end up? Most of them. They're going to end up on the reactant side. All right, so you're going to have a lot of reactants at equilibrium. Okay, so let's look at this. Remember the ideas that we connected here, that rate constant, so small k, is related to activation energy of the reaction. So if we have a really high activation energy, what does that mean about the rate constant? Is it fast or slow? Slow, yes. If you have a big hill to go over, it's going to take you a long time. So that's a slow rate constant. All right, and then what did we say about changes in temperature? What kinds of reactions had big effects of changes of temperature? Yeah, high activation energies were more sensitive to temperature changes. So if you have a high activation energy, okay, so large is more sensitive to changes in temperature because K is already small. Since K is already small, the reaction is already slow. If you give the reaction more energy in terms of temperature, that slow reaction is going to speed up more than a reaction that's already going fast. So if you give an already fast reaction more energy, it's going to go faster, just not as much. So let's actually answer this question now. I guess understand it a little bit more. So when we change the temperature for this reaction, does K get bigger or smaller? So remember, big K is K forward over K reverse. So does K get bigger or smaller when we heat this reaction up? So let's look at this energy diagram. Which direction is more sensitive to temperature changes? The forward reaction or the reverse reaction? The forward. The forward reaction's already going slower, so the forward reaction is actually going to increase more than the reverse reaction. So apply that to this ratio. K is going to increase. The value of K is going to increase. Is that consistent with our Le Chatelier prediction? Yes, it is. So the real answer here, we make more products because the forward reaction rate constant is increasing more than the reverse rate constant. And it has to do with the energy diagram and activation energy associated with this endothermic process. Okay. Yeah, so in the slides in the end of chapter 16, we went over every single scenario, an exothermic reaction, an endothermic reaction, and understanding, okay, large activation energies already have small rate constants. They're more sensitive to temperature changes. Okay, good. All right, so that's basically the conceptual stuff. All right, we're almost done with chapter 15, so let's do this one. Okay, we have a certain all-phase chemical reaction, and we made 2 observations. When the reaction is heated, more reactants are formed. When the volume of the reaction halves, also more reactants form. Which reaction is it? Or which reaction could this be? So this is Le Chatelier's principle, but it's kind of backwards. I give you the observation, you need to figure out what kind of reaction will adopt this type of shift. So if a reaction is heated, so just think about, okay, we have reactants going to products. Where do we want the triangle to be? Just guess and check. Yeah, so if we put let's put the triangle on the wrong side first. So if I put a triangle on the product side, if I add heat, oh wait, no, that's right, sorry. I tried to be wrong. All right, yeah, so, okay, let me do the wrong one first. Let me do the wrong one first, okay. So just guess and check, put the triangle somewhere and look and see, okay, if I add triangle, the reaction's gonna shift to the product. So is this the reaction I want? No, I want to put triangle on the other side, there. Okay, so now look and see, okay, does this kind of reaction match the observation? Yes, this kind of reaction is what? Exothermic, so what kind of sign of delta H am I looking for? Negative, so I can eliminate half of these. Boop and boop. Okay, so it's not those ones. It has to be A or C. All right, so the second observation, when the volume of the reaction halves, more reactants are formed. Okay, so halving the volume of the container does what to the pressure? Partial pressures increase. Yeah, so partial pressures increase. Okay, so how will the reaction relieve itself? It'll move to the side of the reaction with less moles of gas, So let's just look at the 2 options we have. It's either A or C. So in A, which way will the reaction shift? To the product. So is that what we want? Nope, so it's not A. So the answer is C. Because in this case, okay, when we squeeze on the reaction, we're squeezing, the greater pressure on the product side. It's going to shift to the reactant side, which has less moles of gas. So the correct answer is C. All right. So that's Le Chatelier's principle, just a little bit harder because it's kind of backwards, right? I give you observations. You tell me what reaction it is. Okay. I like questions like that. Okay. So there we go. That's all of chapter 15. We have 18 minutes left. What topic do you want to do? Buffers? Okay. All right. All right, let's just go through these and figure out, is it a buffer or not? Okay, you know that's my favorite game, all right? Okay, so what do you need in order to have a buffer? A weak acid and its conjugate base. So let's just say HA and A minus. You need both of them in large quantities, both of them. There's 2 ways to do it. What's the first way? Add both. You add acetic acid, okay? You add acetic acid, and what else do you add? Thank you for saying sodium acetate. Sodium acetate, because what can you not buy at the store? Acetate. You can't buy acetate at the store. You can only buy sodium acetate. Okay, so acetic acid and sodium acetate, that is HA and A minus. Bam, you get mole amounts, plug that into Henderson-Hasselbalch. That's it. Okay, what's the second way to make a buffer? We can start with acetic acid. Okay, we can start with acetic acid. So that's HA. How could I make A minus? You add a base, but what kind of base? A strong base, so you add something like sodium hydroxide. Okay, so when you add sodium hydroxide, you neutralize your HA acetic acid and you make sodium acetate in the vessel. All right. So in case number 2, we're doing a neutralization first. Then we inspect how many moles or millimoles of HA and A minus are present after the neutralization. So with this second type of buffer, what do we have to do first in our calculation? We have to do a BCA table first, but it's not that bad. It's always just a 1-to-1 ratio. So you really don't have to do the full-blown BCA table, okay? Then once you have the BCA table, then what do? Then you do the Henderson-Hasselbalch equation, where the A line is what goes into the base to acid ratio, right? So you have to do the neutralization first, then you plug it into Henderson-Hasselbalch. But if it's type number 1, those values just go straight into Henderson-Hasselbalch. All right, so I won't do these examples. Let me just see if I can come up with some on the top of my head. So if I have benzoic acid and sodium benzoate, okay? If I have, 3 millimoles of benzoic acid and 5 millimoles of sodium benzoate, what type of buffer is this? Yeah, is it 1 or 2? 1, yes, we have HA and A minus. So when you do the Henderson-Hasselbalch, pH equals pKa, pretend we know what the pKa is, plus log base over acid. What's the base to acid ratio? It's 5/3. Yes, it's 5/3. Okay, what if I have benzoic acid and KOH? Let's say I have 5 millimoles of benzoic acid, 3 millimoles of KOH. Is that a buffer? Yes, it is. It's a what kind of buffer? Type 2. Yes, type 2. So what do you got to do with type 2? You got to BCA, then Henderson-Hasselbalch. So will my base to acid ratio just be 3/5? No. You gotta do a BCA table first. So let me just do the BCA table. All right, so benzoic acid, I'm just gonna call that HA plus potassium hydroxide. When you neutralize HA, what do you get? You get NaA plus water, okay? So when you do your BCA table, if I have 5 millimoles of acid, I have 3 millimoles of strong base. What's my limiting reactant? Strong base, so -3. We have 2 millimoles of HA left over. We have 0 KOH. We have 3, so +3 NaA left over. So there's my BCA table. So when I go and do my base to acid ratio in the Henderson-Hasselbalch equation, what is it? 3/2. Yes, it's 3/2. And 50% of your classmates, maybe not our class, the other classes, they're going to put what? They're going to put 3/5. Or wait, yes, 3/5. Okay, but remember, this is a neutralization reaction. We're making A minus in the beaker. Where is the A minus coming from? It's coming from the partial neutralization of benzoic acid. Okay, so let me do another one. So let's do the same one. Benzoic acid. All right, benzoic acid, but I'm going to swap them. 3 millimoles of acid, 5 millimoles of KOH. Is that a buffer? Is that a buffer? It is not a buffer. Yes. Let me prove it in the BCA table. So let me just erase this BCA table. So if I have 3 millimoles of acid, there's 3 right there. There's 5 millimoles of KOH. Now what's my limiting reactant? The acid. All right, so it's -3, -3, +3. So after the neutralization reaction, I actually have 0 HA. I have 2 millimoles of OH minus, and then I have 3 millimoles of NaA. Look at this after line. Is that a buffer? What is present? You have OH minus and you have NaA, which is a base. It's a base. So you have 2 bases present. There's no HA present. What do you need in order to have a buffer? You need HA and A minus present in order for it to be a buffer. So this is not a buffer, but we can still calculate the pH. How would we calculate the pH? The hydroxide, yes, because both of these things are basic, but which one's more basic? The hydroxide. So that's the one we care about. So if I told you, oh, all of this is in 100 milliliters, I have to tell you a volume. We can't just keep it in millimoles. You would just do 2 millimoles over 100 milliliters. That's the concentration of hydroxide. That's your pOH. That's your pH. Right? Where is this on our titration curve? Yeah, so if this was my titration curve, I know we're not doing titrations in this exam, but understanding where this is on your titration curve will help you figure out what calculation to do. So if that's my equivalence point, where is this mixture? Where is it? Is it over here? No, it is over here, after the equivalence point. So I guess kind of, I don't have anything labeled here, but you can infer what I'm titrating. At volume 0, the pH is what? Acidic or basic? Acidic. So I am titrating a weak acid. So I have all HA right there. So our equivalence point is when we've converted all of the HA to A minus, right? In the middle of the titration curve, that is what? That's our buffer. That's our partial neutralization. Those are all the times we do a BCA table, then a Henderson-Hasselbalch. So this example where we start with 3 millimoles of the acid, but we add 5 millimoles of the base, we blew past the equivalence point, all right? And once we blow past the equivalence point, we just assume the pH comes from whatever excess strong thing is there. Yeah, whether it's an acid or a base, depending on what we're actually neutralizing. Okay, so let's do another one. Okay, what if we have NH3, that's ammonia, and we have NH4 chloride? What if we have 0.1 molarity of that, 0.5 molarity of that? What is it? That's a buffer, yes. We got NH3, which is what? A base, and NH4 plus is its conjugate acid. So when we do the base, when we do the Henderson-Hasselbalch equation, what numbers go into the base to acid ratio? Base to acid ratio. Do we just plug those numbers straight in? Yes, we do. So it's going to be 0.1 over 0.5. Okay, but just do make sure when you do the Henderson-Hasselbalch, remember it's pH equals pKa plus log base over acid. Usually this question will tell you, oh, the Kb of ammonia is equal to 1.8 times 10 to the negative 5. And so I'll tell you, okay, the pKb is 4.74. Do you put in 4.74 into this equation to solve this? No, you need to convert pKb to pKa first. Then you can do the base to acid ratio, which is given there. All right, so let's do another one. What if it was NH3? Let's say 3 millimoles of that, and I have 1 millimole of HCl. Is that a buffer? Yes, it is. It is, because adding a strong acid will turn NH3 into ammonium. Yay. And that's a buffer. So when we do the base to acid ratio, what is it going to be? Is it 3 over 1? No, it's 2 over 1. Are we seeing it? It's all coming together? Okay, let's do another one. Let's do another one. What if it was NaA and HCl? 3 millimoles of that, 1 millimole of that. Is that a buffer? NaA is a what? A weak base, because it's the conjugate of HA. HCl is what? A strong acid. So when you add a strong acid to NaA, you make HA. You make it. So this is a buffer, yes. So when you do the base to acid ratio, what's it going to be? 3 over 1? No, it's going to be 2 over 1. Let's keep going. Okay. What if I add NH4 plus and Hydroxide. No, sorry, you can't grab those things off the shelf. Sorry. Ammonium chloride and sodium hydroxide. Let's say 5 millimoles of that, 2 millimoles of that. Yes, that's a buffer. Okay. Yes, so it's a buffer because ammonium is NH4+, right? And then hydroxide is OH-, so when you neutralize that ammonium weak acid, you make NH3 in the container, in the beaker. So when you do your base to acid ratio, what's it gonna be? It's gonna be 2/3, okay? So it's a type 2, in that we partially neutralize it first. Great. All right, what if we had HCl and sodium hydroxide? Is that a buffer? No. What if I have 4 millimoles of that and actually and then 4 millimoles of that? Okay, it's not a buffer, but a neutralization reaction is still happening. So strong acid, strong base. So what is special about this point right here? You've completely neutralized it. The moles of acid is equal to moles of base. Do you know the pH of this? It's 7, yes, because if you think about what you make when you neutralize it, all you have is NaCl and water. If I asked you what is the pH of NaCl, you would say it's neutral, yes, because it's the product of a strong acid, strong base equilibrium. But what if it was 4 millimoles of HCl and 6 millimoles of sodium hydroxide? Is that the equivalence point? No, it's not. So how would you calculate the pH? Excess hydroxide. After the neutralization, what is left over? NaOH. You have 2 millimoles of OH left over. Think about what else is in your beaker. You consumed all the HCl. You made NaCl, but you already told me NaCl is pH neutral, so we can just forget about it. So all of our pH is going to come from our hydroxide that's left over. You just need the volume, you get the your OH- concentration, you get your POH, right? So if we had a mixture of HA, so let's say HF, so a weak acid, HF and HCl, is that a buffer? No, it's not, because it's a weak acid and a strong acid. But if I had 5 millimoles of HF and 5 millimoles of HCl in, let's say, 100 milliliters, could you calculate the pH? Yes. Where would you get the pH? From HCl. Do you care about HF? No, because it only contributes a tiny bit of H+. So we'll just get the total H+ concentration from HCl. That will give us your pH. Okay. All right. Let me do another one. Let me actually go up. What did I want to do? Yeah. Okay. So let's consider a hypothetical diprotic acid, H2A. So there's 2 protons here. There's your K for your first proton. There's your K for your second proton. So what is the pH of a 0.1 molarity solution of H2A? But we have a problem. I give you 2 Ka values. Which one do you use? The strongest one. Also, we want the Ka value that describes H2A acting as an acid. Which K value is that? The first one or the second one? It's the first one. That first one tells us, okay, H2A, all right, pops off an H+, you get HA-. That is Ka1. What is the reaction for Ka2? It's when HA- is acting as an acid. So we don't want to use that one for this example. So basically, this question, it's just like every other weak acid pH question we've done, where it's x squared over 0.1, but we just need to use the appropriate K value. So in this case, it's equal to Ka1, and you've done a billion of those already. All right? Okay, so then this one, what is the pH of 0.1 molarity Na2A? So this is A2-. What is that? What is that? That's a acid or a Base. Yes, it's a base. So we don't want to use a Ka value. We want to use a Kb value. But where the heck do we get it? Let's look. Yes, we get it from Ka2. Why? Because A2 minus is the conjugate base in only Ka2. Yeah, so we take that value to get Kb. So what would Kb be here? We take that Ka2 value, so it's 10 to the negative 4. All right, so that's the value we use because we have A2 minus present. All right, so then you do the same calculation. It's x squared over 0.10 equals Kb2, so that's equal to 1 times 10 to the negative 4. All right, but when you do the calculation, you calculate x. What is x? The concentration of OH minus, yes, and you get POH, you get pH. All right. Good luck on your exam and your studying.